Next, we will have machine learning on energy consumption prediction by Mr. Benny Huang here, and MicroPython by Mr. Patrick Char in P4701. You may now proceed to the respective panels for the doors at the back. And remember to bring along your personal belongings with you. If you may encounter any inquiries, please let us know. Thank you. Okay. The session about machine learning on energy consumption prediction is actually a project in Hong Kong U Deep Learning Lab, which involves different machine learning approaches and comparison. Our speaker, Mr. Benny Huang, is now studying computer engineering in the University of Hong Kong. He enjoys coding and wishes to make the codes better. May I now pass the time to Benny. Benny, please.
Hello. Is it working? Oh yeah, cool. Okay, so I think I have to say sorry in advance. I didn't feel good in the morning, so my roommate gave me some medicines, and that's why I feel a little bit dizzy right now. So if I make any mistake, please correct me. And if you have any questions, you are welcome to bring them up during the question sessions. Okay, so shall we start? Okay, so some very brief self-introduction. I'm Benny. I'm studying computer engineering in HKU, and I'm currently year 3, and I'm from Taiwan. So if you find I have Taiwanese accent instead of Hong Kongese accent, that's why. Okay, so it all started with a company called Blue Sky. Blue Sky is actually a startup, but despite being a startup, they are able to collaborate with many large institutions. So they actually got a large amount of energy consumption data. And I think roughly 1 year ago, they just come to our professors and ask my professor, say, hey, I have this large data set, and we want to build a machine learning related project based on this data set and integrate this system into our current system. So, hey, what do you think? Do you think it's doable? My professor say, yeah, of course. So let's do it. And so we initiated this project, and actually I was not in the project initially. I was added to the project later on, and there are also several others MSc students in the project. And because I'm very little bit more experienced on that, so I'm usually the one who have to handle many things. Okay, so after discuss with the Blue Skies, we settle our objective. The first is to understand the patterns of the test energy usage. So we hope to use some approach to identify like when the graph goes like this or goes like that, and when he have these patterns, this characteristic, and what might it means, yeah. And try to use the conclusion in the first point to do forecasting of the energy use in the future. And then what Blue Sky emphasizes is to integrate the models onto their real-time systems, and they have the systems that can display and decide some policies to their clients. Okay, so I should also introduce about the data content. It's a pity that I cannot show you the detail of the data because we have the non-disclosure agreement. But like here is the general information of the data. So we have power consumption records in 78 different regions, and for all these different regions, they really contains a lot of places that for different usage. For example, the office, the school, the warehouse, the kitchen, and like experimental area. So like for some children go there and experience different career life, like what made this kind of career life be. So there are a lot of different, very different usage for those regions, and that is very valuable for a data set. We got to see a lot of different patterns when people are in certain environments. Okay, the total durations up to years, relatively long, and the item includes different categories, including AC light socket. And that's the point, because nowadays you seldom get this kind of detailed data set that measure the least detailed information in the, no matter it's like large or small regions. And the time interval can be up to minutes. So it's very detailed. It's really very detailed. And actually, me and our professors, like, we don't really see this kind of like detail data set. And usually when you go to government or go to other statistics centers, they have the data in day or in month or in years scale, and for the whole Hong Kong regions or for the whole Hong Kong islands. So that's what we find this data set to be very interesting. It can be very detailed, and we got to see very interesting patterns of the human behaviors. Okay, so yeah, of course, our hardware. And in our lab, we set up like many different GPU server, and the server have different like kind of GPU. Like the newest one, which I composed, is like 1080 Ti, and we also have some like older version, Titan X. I think it's like about roughly 2 years ago, relatively old. So you know, we have a lot of this kind of stuff, and with these computation powers, we got to play a lot of different models with this data set. Okay, so you remember we have like 3 objectives. The first is understanding patterns. So we do a lot of visualizations. Well, it's quite sad that I'm not able to show you this plot because, well, you know, but I think that's fine. You see the speaker for Matplotlib is sitting there. So I think it's fine. And so we will jump to forecasting the future energy usage directly. Wait. Oh yeah, so after some discussion, we decided to use the past minute data to predict the energy usage for the next hour. And we choose this kind of predictions because we think that is doable, and the Blue Sky thinks, okay, that is applicable. Because if we only predict like for next minute, it's sort of meaningless, you know, it is not useful. Okay, so for input data preparations, there are a lot of like stuff to like pre-process the data. For example, we encode the time data. We have like hour and a minute, like 2 informations. For example, we combine them into like 0 to 1440 for each date, and there are a lot of other kind of like re-encode of the time data, and we find it quite useful when we feed this kind of re-encoded data into the model. And temperature and humidity and holiday informations are not included in the data set, but we just grab it because after some observations, we find that, hey, this information may be useful for the models, for our AI agents to predict the future usage. So especially interesting for the holiday informations that, like, you know, greatly drives up the accuracy. And for model selection and fine-tuning, we decide to go for LSTM first because, you know, it's time series, and when it goes with time series, like, well, we directly think of LSTM. And also because our data period is quite long, so we hope to, like, initially we hope to input this like long series of data into LSTM, and we really hope it can find some long-term patterns of the energy power usage. And also we have to result reviewing and to see like how to enhance our results, like based on the prediction result they give us. Okay, so yeah, so first, like, we goes about LSTM. So LSTM is basically a form of recurrent neural networks, and I believe you already see this plot yesterday. I think another speaker like download this plot at the same place as I do. So I don't think I need to explain what is RNN, but like we can go a little bit more details of this structure. Alright, so you know, it maintains its state. Can I see? Oh, I don't have like. Okay, so like the upper like horizontal line is the state. So the network will like how to say keep a state in the neurons, and then the second horizontal line is the prediction result from last node. And so what it does is like it have this input, and it takes less input to concatenations, and then it will multiply it with we call forget gate first. So after multiplying with the forget gate, it produces a forget filter, and then they multiply the forget filter with the previous state, and you can see that because usually we use these sigmoid functions, so the absolute value is like something between 0 and 1. And so if the forget filter is somewhat near 1, and that means this node decides to let full information of like this number to pass through. And if that number is very close to 0, that means, well, we decide to forget this part of information. Okay, so this is the input gate. So again, concatenations and multiply with the input gate and have an input filter, and concatenations to do the input. And this is the hyperbolic tangents, which result the range in -1 to 1. And then here is the output gate. So also do the concatenations and multiply with the output gate, and then we have the output. So that is some like detail of this model. So we know how this model works, and there are research paper indicating that the forget gate is kind of like most significant within the 3 gates like we have. And also to eliminate the gradient vanish problems, they use additions. There's addition there, and so you don't have like gradient explosion or gradient vanish problems. Okay, so as I said before, we hope to see is longer input data series better for the prediction. And well, if yes, like how does it help? And we really want to see like how and why, because when we only know how and why, then we can use like this kind of like human logic back into our energy policies within like certain regions or certain buildings and like that. And well, if the longer input data does not help, then how do we improve the model? So we decided to, we use LSTM to achieve a reasonably good accuracy. I mean, compared to random forest, vector machines, and those gradient boost stuff. And we hope to see like how this like long input data like help the model do the predictions. So we hope to inspect the model and the behaviors. And I think this does not work. No? Okay. Then I will. Oh, what the heck? Hey. Okay, that's weird. Like, I'm opening the browser and it's not responding there. Should I refresh it or something?
It seems that it. Yeah, I see. It's it seems used to mirror the screen, but it turned out that you put the screen side by side mode and mix the mouse.
Because it works when I tried previously.
Oh, you try to put some
Okay.
synchronized both.
Okay. Yeah, it works.
Then that should work.
Okay, cool. So it works now. Okay, I think later on there's a workshop to teach you how to use Keras, right? So maybe it's a little bit earlier to talk about this, but like this is the source code of Keras, and you see here is the function build. This script is for the recurrent neural network, and this build function is in the LSTM cell class of the Keras source code. So when you add the layers and you add the LSTM layer into a Keras sequential model, that is the function it called build, and yeah, it just initializes a lot of things, and then it add this. Here's a point. It add the weight to the model. Okay, so here you see here is the input dimensions and the self units times 4. What is the 4 means? The 4 means the input gate, forget gate, output gate, and the kernel state, the kernel gate. Okay, so you will add the weight for the current input. So it's right input dimensions, and then you have a recurrent kernel. The recurrent kernel the shape will be the numbers of units, because it will be the last input from the last output from the last input node. So mathematically we will do a concatenations, but in Keras source code it just uses 2 weights to like sort of like combine these computations. And then here is add bias where is supposed. Okay, so it adds the weights and the name is bias, so you can see that the dimension is the unit number times 4. The 4 is also forget input, output, and the kernel. In Keras, when you have the model, you just like load the model into a memory, then you call dot get underscore weights, WEIGHTS, and then you get a lot of layers of different weights, and then we can like extract like those certain weights, and then we can see. Okay, let me find it. Okay, step. Okay, step is a function that when Keras do when you do the real computation. Okay, so here is the real computation power, where the real computation happens. Okay, so you get the weight that you see in the previous functions, and those weight is like the dimension is like unit times 4, right? So the fourth means the first part is 0 is the input gate. And the second part is the forget gate. The third part is the sales gate. Then the fourth part is output gate. So if you have like 100 units in these neurons, so you will find that from 0 to 99 is the input gate. From 100 to 199 is forget, and from like 200 to 200 and so on, and so we spend a while to visualize all this stuff and to see what is going on, and then we. Hold on, let me see my notes. Okay, and then we do a lot of visualizations, and then we realize that the value for the forget gate is a lot lower than we expect, or how to say, a lot lower from my experience when I'm building other projects. Well, that somehow means that the model tends to forget most of the informations that when we currently pass through the informations, and that is actually not good. But here's the point: like, don't just take average of the forget gate, because the matrix hides in the distribution of the those gates, and it's basically a black box, so it's relatively hard to identify the relationship of the parameters. But just like I got a feeling like, oh, it's a lot lower from my experience, and it should have been like this. And so we try to see what is happening, and then we try to decrease the input length for the models, and then we find a very sad thing, that when you reduce the length of the input model, the accuracy does not go down. So that means like when you input the previous 10 days, you will forget the previous 9 and 1,420 minutes. And the accuracy only goes down when the input length is like less than 20 minutes. So what does it mean? It means like you only use the 20 minutes to predict the average load for the next hour, and which is kind of sad. Okay, so we also like try to see like what happens when the numbers passing through the Keras models, and we think that okay, so in the previous 20 minutes there may be something happening, and maybe like this, okay, that's our explanation. Okay, that's our explanation because we don't know what is really happening on. And our explanation is like when certain data patterns happen, that means a group of people like they enter this room, they live this area, and so it will affect the energy usage for the next periods of time. And we guess what the model learned basically is what happens in the previous 20 minutes, and then it directly predicts like those future usage from what happens in the past 20 minutes. And if there is anything that happens regularly, the information is already encoded into the time data. So previously, I already said that we re-encode the time data to make it more efficient for the models to get the information from those time numbers. So if some activities is happening like once a day, and for example, like people have to go to an office, like they arrive at the office at like 9 o'clock, and at 8 o'clock, the model will use the time value to already know, okay, at 9 o'clock there will be people coming in, so the average usage will goes up later on. And those kind of like regular patterns are already encoded in the time value. Okay, so that's what we found. And then we think the model identified the patterns, the series patterns of the input series. So then we think, well, there may be other things that can help on this stuff, which is called convolutional neural networks. And for those who are not super familiar with this kind of CNN, it basically uses filter to like scan through like if this 4 node is something, okay, like if it's a X or if it's a circle or if something, and then it uses this filter to scan through the whole plot. Okay, so basically like when they do object recognitions, they use this kind of convolutional neural network to scan through, and then they will see like if this object is contained in the plot. Okay, so like we think, okay, if the models, basically what the models do is to identify the patterns of the time series, then why don't we just use a convolutional neural networks to do this kind of jobs? And in the in the graph, like they basically use 2D convolutional neural networks, but in Keras they also provide a 1D convolutional neural networks which can be used for time series. Okay, so like you can go to a reference if you are very interested in this stuff. And our conclusion is that the CNN can also do a great job of recognizing the behavior patterns. The accuracy does not go down, and well, it didn't go up either, but we achieved roughly like 10 times performance enhancement. So like it maybe takes a few days, like when we are doing the trainings on the LSTM, and when we use CNN, it achieves the same accuracy with just a few hours. It's like a very huge performance enhancement. Okay, so that's basically the end of the story. Like my personal conclusion is that we will still need like more advanced RNN that can extract the better patterns data, so that we can reserve the characteristic of CNN while still remember the long-term informations in the past. Okay, so after we get these models, we have to integrate our these systems onto what Blue Sky get. Okay, cool. Onto what Blue Sky get. So like we use our GPU server, and Blue Sky, they have their own cloud and they have their sensors. So we use the like S3 and EC2 and as our platform to do the communications. Okay, so here are some like short notes for young data scientists, and a disclaimer is that I'm also one of the young data scientists. So this part is not very useful if you are already a very experienced data scientist, and my opinion may not be very useful. But what I noticed is that recently, because data science is only a field that appear to be popular and in a recent 5 to 10 years. So in Hong Kong right now, there are a lot of like very junior data scientists, and they just start learning. They just start learning things, and there are many of the data scientists are so young, so they are actually not sophisticated engineer before they become a data scientist, and that more or less cause some problems. Okay, and so the first thing is like you have to understand your data more. Like previously, I saw a post. It was sharing it was sharing the experience to predict the university entrance results. And he basically only used like 2 inputs. I think the one is SAT score and GPA, and to predict if he will get into like be accepted by the university or not. And then he used TensorFlow, like 30 lines of code to use the TensorFlow, build a multi-layer perceptron, and do this job. But actually, sometimes like you don't have to relate everything to deep learning. And with these like kind of like small models, you can use like logistic, and you can use this decision tree, and they will work well, I believe. And also visualization is also very important. Like what very young data scientists will often ignore is like this kind of very basic stuff. So like you have to understand your data more and don't relate everything to deep learning directly. And you have to know why and how it is happening. And this is extremely difficult because many of the machine learning algorithms, they're actually black box. So we are actually required to have like more mathematical background to achieve these things. So well, I'm still learning this, but the second and third point will be, at least I think, will be how you evaluate a data scientist. You know, you have to know like how to evaluate a result. When the model gives you a result, you have to know what model is doing. And when you know what model is doing, then you can know like how you can help the model to achieve better accuracy or achieve like better results. And sometimes you can even explain like why this is happening and how this is happening. And for many of the institutions, actually why and how is what they care the most. Yeah, so there's an example like previously I have a project with Hong Kong government, and they provide us also a data set, and then we use the models to achieve very good accuracy. Like our professors and the other researchers are like quite amazed by the accuracy, but eventually that department is not interested in our results because they say like, okay, so I know what I know this is going to happen, but how do I stop it? Because I don't want it to happen. So you have to tell me like why this is happening and how this is happening and how do I stop it. That's why I care. You can't just tell me like this is happening because we know this is happening and then we just sit there and it still happens. Okay. So what we do is actually we adjust our model into a very minimal structure. So like we are able to reason about like why and how. So actually the accuracy decrease a bit. And it's not the best accuracy we can achieve like from an academic viewpoint. But for that department, it actually be very interesting because this minimal structure of the machine learning algorithms is able to help them to improve their real world application works. Okay, so I think why this is happening and how this is happening is very important to us. Okay, so and the modularization. So you will see when you read like articles on Mediums and when you watch the YouTube, then you will find like, oh, they just finish a whole script without defining any functions. And if you are an engineer in Java, then you will find like first thing you learn is to define class, and the second thing you learn is to define method. But Python is so powerful, it's so elegant that you don't really need to have those kind of like very troublesome stuff. Then you can achieve amazing stuff. But actually, if you really finish like 200 lines of the data science script without defining functions, then you will find it very, very trouble when you want to change your like the preprocessed method or your models and these things and so on. And so I think one tip I want to share is like do spend time on modularization, like define clear interface when you are loading the models, when you are formatting those data, and when you are doing normalizations, how you build the models, how you evaluate the models, how you store every result into a package. Define interface and define the data that have to pass through the interface. And when you need a new things to try, you can then swap those methods very quickly. And that is, I think, how to significantly increase the working efficiency of the data scientist. And this is not about managing like 10,000 or 100,000 lines of code. No, it's not. It's just about managing 200 lines of code. With each 10 lines of code, you will have like 1,000 different of combinations you can ever imagine. And that's what is data science differs from other engineering fields. Okay, yeah, so I love this graph. So like for us, like we should really like reduce our time on the coding. We should let the computers do most of the things. And because like, you know, when we are doing this kind of stuff, we have to like know a lot of math and read papers to see like what's library and what algorithms are there showing up. Yeah, so like I think I would say like when we can start to achieve like better modularizations and we can achieve like better efficiency when changing the code, then we will be able to do a better job, and this industry will become more mature. Yeah, and the final thing is testing case. So actually there exists a million different ways you can see your loss decreasing and see your accuracy going up, but nothing is going right. It's possible that your data should be filled in like shape of this, but you know, Python and pandas, especially for pandas, they actually tolerate a lot of mistake you made. So maybe you want to fill the data like this, but the panda actually fill the data like this, and like, okay, you know, the model always learns something out of like everything. And also, you know, like when a function accidentally returns 0, and you put that 0 into a pandas column, and in a panda, if you call a column and you assign it to a value, and if that value is an integer, it will fill the whole column with that integer. And then you wonder, okay, I think this column is very important for model, but why it doesn't learn anything? And that's because your previous function accidentally returned a 0 instead of a list. So Python is a dynamic programming language, so it don't alert you when a list should be returned, but you accidentally return an integer. It won't tell you. Okay, so adding testing case wherever you can, and also visualization is a very good way to check if your model is really working. Okay. Ooh, I'm pretty good at controlling the time. And this is the end. And you can ask any question if you want. Yeah, sure.
Very good presentation.
Thanks.
So just two quick questions. The first is just to understand the problem setup a bit better. So you're thinking that if we have the temperature and humidity, and we can predict the energy consumption.
Because our energy consumption data include a very important stuff called air conditioner. So usually air conditioner, the usage of an air conditioner tend to goes up, like when the temperature is actually up. And this is something that will not, this kind of information will not be disclosed by other kind of energy consumption. And if we provide, so this is the characteristic of a model. It does not learn everything from nothing. Like you have to provide information, and then it will extract the right information out of the information you give it. So like you have to give it something like it can learn. So it can learn. So that's why we put temperature and humidity into the model.
Thinking from a practical application.
Yeah.
So if the blue sky is trying to predict the next, say, an hour or a period of the energy consumption, then they need to also predict the humidity and temperature.
The humidity and the temperature is actually from the previous hour, the previous minute. Yeah. We find the temperature and the humidity data from the previous period is better for it. It's better for it than the previous AC consumptions. Yep. Yeah, sure.
So what do you envision if it actually is working in the real time? So basically every time it has a next, say, an hour of data, then you put all that data into a training set, and then you retrain the whole model and then predict the next hour. Is that how it's going to work?
No, we train 78 models for 78 different regions, and then it will somehow works like this. Like the model is just there, and when we have a scheduler, so that when the time's up, then the program will like start itself and load the models from the disk to the memory, and then it will grab the newest data and to do a prediction. And after the prediction, it will go back to sleep. And like for example, like after a week or after a month, like we get new data, then we will have another process to retrain. So this is from engineering fields. Yes. Oh yeah, sir.
What is right now the time scale of your video set? How often do you take a video sample?
Like how often do I?
Or the time scale of the LSTM is the same, because seems to me it's not learning the time sequence right now.
We input the previous 20 minutes in.
20 minutes. How often do you sample the figures?
Each minute.
Each minute.
It means like we input like 20 minutes.
20
So
minutes it means 20 steps of LSTM.
Basically, yeah.
Because it seems to me, of course, you cannot show the accuracy results, but that is not really learning anything on the time sequence. And my question is, do you really need the time sequence, or is just a fact that in the previous 20 minutes something is happening or not?
Yeah, we believe that the model learning is that in the previous one, because we sample each minute, so it's basically like the data from like the 30 minutes, 34, 35, 36. So we have like previous 20 data points.
Even in the
And
previous 20 minutes, is it learning really a sequence, or what? Is it just looking, is the temperature higher than this or not, or just looking at series of events without
you mean does it look into it for a whole sequence, or?
To me, using the sequential information from what you say, if I put a CNN
Okay. I believe.
doesn't change.
I think like LSTM may not be that good at doing the sequential learning. I mean, it's like.
No. What it seems to me is that the sequence doesn't carry any information. Maybe you just need the features over the 20 minutes. Or you need, yes, a sequence, but over much bigger time steps that you can analyze with CNN.
It means the data we provide to the model can
There's
be.
no information in the sequence of samples you take. It's just the fact that whether in the previous 20 minutes, for example, the temperature is high, or someone entered in the room, or whatever. Not the sequence of events. It's just the events you need, not the sequence. If in the last 20 minutes something happened or not.
But like you need sequence to tell you the events, right? I mean,
No, you can just take the figure set and
take a what? I mean,
you don't really need the sequence. If you say it's not providing any extra
Well,
information.
I think it is, because what you're looking at is very similar to a chemical process, right? So currently this temperature is 20 degrees. What happens in next our horizon will depend on the current state and the current temperature.
Yeah, it
Plus
depends on the past, of course. But
for whatever impulse that come in. So I think I may miss something. What he thinks is he finds that the more recent information is more useful to predict the next hour horizon.
Yeah.
But which makes sense when you look at how.
yeah, no, I agree on this. But then he say that when you took a CNN and just do an average or max pooling, you get exactly the same. So you lose much of the sequential information about the previous 20 minutes. It just
no, the CNN actually learns the sequence. The CNN can learn the sequence. The CNN use a filter to scan through. So it will know like this 3 minutes is like this and next 3 minutes is like this. The CNN actually does learn the sequence.
By 10 minutes, but
Yeah.
you average everything, and so you lose the information between the first 10 minutes and the second or the fourth 10 minutes window. There's no overlap. So
The design purpose of the LSTM is to learn the sequence, and I think
yeah,
the
what I see right now is that the sequence is not very important. If the CNN is going to give you more or less the same results.
no, but when the CNN scan through these figures, when the CNN scans through, the CNN will also detect like when this data point is increasing or is decreasing.
Decreasing,
Yes.
yes. Not on time scale of an LSTM. It's much shorter.
Yeah, I think it's possible.
I think maybe you just need that. You don't need to know what happened, what is the relation between what happened at the minute number 20 compared to the minute number 0 in the past.
Yeah, that is possible. But because in CNN we use a relatively large filter. I mean, it's not 1 times 1.
I can tell you what happened if you use a filter of time 1.
Or pardon?
Just a filter of time 1. So
No. We didn't use a filter of size 1. We used the larger filter. Yeah. Maybe we can try that on, and yeah, maybe.
filter of time 1 and then you average or max pool depending what works better.
Yeah. We can try that. Yeah, definitely we can try that. There are so many things to try. We just don't have time to try everything. Yeah. But yeah, that's a good idea. We can try that.
Thank you, Benny. Since our next session is starting soon, maybe we can discuss with Benny afterwards.